Hello everyone, welcome back to Chapter 1, Reactions Kinetic. In this video, we are going to talk about subtopic 1.3, Factors Affecting Reactions Rate. Here's the learning outcome. By the end of the lesson, you should be able to explain the effect of the following factors on reactions rate, including concentrations of pressure under one factor, temperature, catalyst, particle size. Illustrate the effect of temperature on reactions rate using Maxwell-Boltzmann distribution curve, and to compare the curve of the energy profile diagram for reactions with and without catalyst. So here's the first part of the video. So the first factors that affecting the reactions rates is the concentrations or pressure of reactant. When the concentrations of reactant increases, or the pressure of reactant increases, the number of molecules of that reactants increases. As a result, frequency of effective collisions increases and the rate of reactions increases as well. Similarly, if you have a lower concentrations of reactant or lower pressure of the reactant, number of molecules will be lower. Therefore, frequency of effective collisions decreases as well as the rate of reaction. Bear in mind that the keywords that effective collisions is important. So please highlight the keywords effective. The second factors that affecting the rate of reactions is the particle size. So when you have a smaller particle size, the total surface area increases. Therefore, the frequency of effective collisions increases and the rate of reactions increases. If you have a bigger particle size, total surface area becomes smaller, frequency of effective collisions decreases, and the rate of reactions decreases. The third factor that affecting the reactions rate goes to temperature. So remember that temperature will always link to kinetic energy. So here is the keywords. Okay, KE stands for kinetic energy. So when you have a high temperature, the average kinetic energy increases or become higher. So the number of reactant molecule with enough kinetic energy, which is equal or greater than the activation's energy, will increase. As a result, the frequency of effective collisions increases and the rate of reactions increases. Bear in mind that number of reactant molecule with enough kinetic, this one is you need to have a very minimum energy to at least overcome this activation's energy. For the effect of temperature, there is a diagram that you need to familiar with, which is called as the Maxwell-Boltzmann distribution curve. Okay, take notes on the spelling, Maxwell-Boltzmann. Will be discussed in detail in the next slide. The last factors that affecting the reactions rate is the effect of catalyst. A catalyst is a substance which increases the reactions rate by providing an alternative pathway with a lower activation's energy. So you have a lower energy required to produce a product. So the effect of catalyst, we will use the energy level diagram to show how the effect of catalyst can increase the rate of reaction. So you need to show the curve with or without catalyst on the same graph. So over these four factors that affecting the reactions rate, concentrations and particle size is quite straightforward. But temperature and catalyst, you need to use the diagram. Maxwell-Boltzmann for temperature, energy level diagram for catalyst. All right, so let's just look into more details about effects of temperature using Maxwell-Boltzmann distribution curve. So here's the diagram to represent this Maxwell-Boltzmann. Y-axis over here, you have fractions of molecules. Sometimes it can written as the intensity, which will refer to the number of molecule you have in the reaction. Okay, number of molecule against the kinetic energy. So in this diagram, you have two curves. The first curve in blue color represents the reactions happen at low temperature. Okay, the red color refers to the reactions occur at high temperature. And this dotted line is very important. Okay, it refers to minimum energy needed for reactions to happen, which is your activations energy. Okay, your EA. And what is more important is this area on the graph, the one that's shaded over here. So this shaded area represents the total number of molecule which has the kinetic energy equals or greater than the activations energy. That means beyond this point, okay, those are shaded under this area are the number of molecule which successfully overcome the activations energy and the reactions happen. Okay, so in the explanations, when temperature increases, average kinetic energy of the molecule increases. Remember that temperature always linked to kinetic energy in your explanation. So temperature increase, kinetic energy increases. Therefore, the number of molecule with energy equal or greater than activation's energy EA increases. So the second point here refer to the shade area on the graph. Okay, the shaded area. So high temperature, high kinetic energy. So more molecule with enough energy. So the frequency of effective collisions increases, rate constant increases, and the reactions rate increases. So rate constant, if you still remember previously we talked about temperature will affect the equilibrium constant. So for rate constants will only be affected by temperature. Rate constant increases when temperature increases. Alright, so next is the effect of catalyst, in which we need to use energy profile diagram to compare between the reactions that use catalyst or without catalyst. Okay, so here is your energy profile diagram. We have the potential energy or energy against the progress of reactions. So over here, we have reactants. Okay, and then this one will be your transition state, whereby you have your activated complex and then you have your product. For the reactions that without the use of catalyst, the activation energy is higher. That means you need more energy to overcome so that you can proceed to form the product. But if you added catalyst, okay, the functions of catalyst, recall that is to increase the reactions rate by providing an alternative pathway with lower activations energy. So now, if you use the catalyst, you only require maybe half of the energy to reach your product. All right, so show these two curves in the same graph. So the one with catalyst or without catalyst, so that you can compare. Okay, show both curves on the same graph. Define what is a catalyst. So definitions just now. Increase the rate, providing alternative pathway with lower activations energy. Alright, so example questions 1, we talk about effect of catalyst. So the data for decompositions of HBr to H2 and Br2 is shown in the table below. So in the first sentence here, it gives you the reactant HBr, and then the product is H2 gas and the bromine gas. So given the data, you have your enthalpy positive. So over here, you know this is an endothermic reaction. Energy is absorbed. And then you're given activations energy 189, 160 without catalyst and with catalyst. So first explain the functions of platinum. So this platinum is actually your catalyst. So define platinum will increase the rate of reaction by providing an alternative pathway with lower activations energy. Okay, you can refer to the notes. And then the second one, based on the above data, sketch and label energy profile diagram for the decompositions of HBr with and without catalyst. So practice using the values. All right, and then number 3, to calculate the reverse activations energy for the reactions without catalyst. Okay, so reverse activations energy. Recall that in our chapter 1.2, we talked about the reverse activations energy. So this is the energy between product and the activated complex. So in this case, you have your y-axis, which is your potential energy in kilojoules per mole. And the x-axis is the reaction's progress. So since this is an endothermic reactions, so you have a lower energy for the reactant and higher energy for the product. So this one is reactant, this one is product. Okay, and then label this one as the transition state, or you want to label as activated complex, that's fine. All right, so we label the delta H first. So since it's a positive value, so your arrows goes from the reactants towards product. It's an upwards direction. Okay, positive 65 kilojoules per mole. And then the activations energy between your reactants and the transition state. This one is the one that without catalyst. So 189 kilojoule per mole without catalyst. You need to label everything that you draw in your energy profile diagram. So this curve represents the reactions without catalyst. But when you have the catalyst, the activations energy become a little bit lower. Okay, so reactants and products are the same, then you just add another curve over here and do your labeling. So similarly, between reactants and the transition state over here, you have your activations energy 160 kilojoule per mole. So label with catalyst. Okay, so this is a complete label diagram. You remember to have your axis. You just add on over here. This is your progress of reactions for x-axis. So for number 3, we want to find the reverse activations energy. So remember that reverse activations energy is between the product and the transition state. So we are looking at the one without catalyst. Okay, so between the product and the activated complex at transition state. Okay, so this is your reverse activations energy. We label as EA prime reverse. Okay, so do a simple mathematics. The EA is 189. The enthalpy is 65. So the EA prime for reverse reactions without catalyst equals to 124 kilojoules per mole. Okay, so this one is for the endothermic reactions. So be careful. Sometimes you are going to draw the energy profile diagram for exothermic reactions. So be very careful about this delta H, whether it is positive sign or negative sign. So the shape of the curve will change.